So today, what we're going to look at is we're going to put all of this information that we just got out of this lab together, and we're going to be able to define the written part of our model. After this, we're going to be able to go back and look at how our chemical bonds are put together using Lewis dot diagrams, and we're going to be able to look at the physical part of our model. So, in order to finish up the written part of our model, let's keep using the potassium hydroxide as an example. I really like that one. So that was our KOH, right? And this is really saying that I've got potassium at a positive 1 charge and hydroxide at a -1 charge. And that's being put into water. So I'm going to write it this way. I'm saying that it's being put into water. That's the only change that's occurring. And when it goes into that water, it dissolves. It breaks up into these two components. And so on the other side, I've got K plus OH minus. But now there was also a lot of heat, a lot of energy that was released in order to raise the temperature of this water. So I'm also going to say that there was, I'm going to use red for this, plus heat. If I were to do the ammonium nitrate, then I would say NH4, NO3, being put into H2O, made NH4 plus NO3 minus, and then we put plus, and then we put a negative heat. So when the ammonium nitrate went into the water, it absorbed heat from the water. Now why is that? Why does that happen? Why are these, when it splits up, why is it releasing or absorbing heat? Well, the reason is that this water already has, remember, we've got this little beaker that we can draw out, just saying that we've got little water molecules that are moving all over the place. It already has its own certain amount of heat. When we put these into the water pulls them apart. And so each of these little water molecules is basically creating a new bond with each of these parts. That bond doesn't take as much energy. So remember, we have these things called chemical bonds. If I've got the potassium hydroxide, and I've got them both together, I've got their charges, those charges make them hold together. It makes them want to stick together. So there is some energy in that. We call that potential energy. We'll say potential, and we'll say potential chemical energy. So these bonds have potential chemical energy. And when these bonds are broken, that potential chemical energy gets released. However, if I've got the K plus and the OH minus, then the H2O is going to surround these in order to dissolve them. This is going to be the opposite. The O's are going to face the K plus. So when this happens, these substances get pulled apart, and we have new bonds. These aren't quite the same as chemical bonds, but they're very close. So we have new bonds holding these together. If this bond has less energy than this bond, then we have excess energy just getting released. And where's it going to go? Well, there's only one place for it to go. It's got to go into the kinetic energy of the H2O moving around. So as the H2O dissolves the potassium hydroxide, as it dissolves this substance, as it breaks this chemical bond, it forms new bonds, and then it starts to run around. So it's like a crowd of people all hanging out together, and then people start being pulled away from the middle of the crowd. And if someone grabs their hand and pulls them really hard, they both have to start running really fast. It's kind of like that. As they get pulled away from this crowd that's not moving that much, they get pulled away with a lot more velocity, with a lot more speed. They have to start moving faster. So we can see that as these bonds are broken, if the new bond does not have as much energy inside of it, if it's not storing as much energy, well, then we're going to release that energy as heat. That heat has to go somewhere. It has to be absorbed by something. It's not just going to move around the earth just dancing to and fro. The water is going to absorb that and get faster. So when we write out these chemical equations, we write out that it either added heat, it added energy, energy was released into the system, or it absorbed energy from the system. And by system, I mean really its surroundings. So when this potassium hydroxide breaks down, when it gets dissolved by the water, it's going to release this pent-up energy. Okay? So for our purposes, we are going to just write either positive heat or negative heat. If I want you to write one of these down, one of these equations down, and say, okay, was heat released or absorbed? When you write this down, you should hit added heat if the temperature went up, or subtracted heat if the temperature went down. Okay? This is really a pretty simple way to think about it. It's subtracting heat, well, I'm taking heat away. So on this side, I've taken that heat away. We are negative heat now because we got colder. We have specific names for this as well. Those names are endothermic and exothermic. An endothermic process, so this one is going to be endothermic. You should write this down. Endothermic absorbs energy from surroundings. AKA, in other words, gets colder. And the other version is exothermic. An exothermic reaction releases energy. To its surroundings. AKA gets hotter. Gets hotter. Okay. So that's vocabulary that you're going to need to know. You're going to need to know exothermic and endothermic. Okay? You're going to need to be able to write out an equation, which we've done plenty of, but be able to add in this plus heat or this minus heat. Okay? Now, chemists are actually able to go a step further with this heat and figure out the exact amount that gets released. And when they do that, they don't just figure it out per gram. Because remember, these things have their own individual weights on the molecular level. I could draw this out and it would be, one of them would be larger, one of them would be smaller. NH4, look at this, looks like this, and it's a positive. It's going to be hanging out with NO3. Double bond in here somewhere. I don't remember where. NO3, just like this. This is much larger than just this guy. See that? I mean, oxygen's pretty heavy. And there's 3 of them here. There's only 1 of them here. So the difference in these weights is actually fairly significant. This one is 56.1 grams per mole. Remember when we talked about moles? That was a massive number of these individual particles, enough that we can actually weigh these out and keep track of how many there are. The NH4NO3, that is 80 grams per mole. So what a chemist will do is they'll figure out how much energy was lost for each mole of a substance, not just for the grams of that substance, so that they can figure out how much energy they might lose in a different reaction. So they're able to figure this out and really track these energy changes and put a lot of numbers to them so that they can make big predictions. Now, a really regular application of this might be a rocket scientist or even just a car auto engineer looking at different possible fuel sources, right? Gasoline has to burn. When it burns, it releases some amount of heat. Well, is gasoline the best fuel for a certain application? Well, they need to figure that out. So they'll look through, they'll write out the equation saying, okay, well, I've got, let's just say I'm trying out methane, which is just CH4. When that combusts, it's gonna combine with oxygen to make H2O. Remember, we looked at these in our last unit. It's gonna make H2O and carbon dioxide, and it's gonna release a bunch of heat. Well, a chemist is going to want to be able to look at exactly how much heat that releases, and they're going to want to look at that in terms of moles. Why? Well, think of an engine. An engine has a certain amount of space where it combusts the fuel. They need to know how big to make that space. So if it's, 20 milliliters of space to combust that fuel, it's going to release a certain amount of heat because only so much fuel can fit in there. So this is why chemists want to look at these equations like this and know how much energy is being traded back and forth. And this is how they would actually go about putting numbers to this. Now, I'm not going to expect you guys to put numbers to this. That's a little more advanced. But I will expect you to be able to identify. If I tell you a reaction is exothermic, I'll expect you to be able to just tack this on at the end, that it's got heat being added on the outside. And if it's endothermic, then it's got heat being taken away. Okay? All right. So next, I do want to show you an actual textbook that would have some of these values, some of these heat values for different bonds, just as something to kind of show you this information going forward. Not necessarily something that you would be able to do.
Okay, so this right here is the Handbook of Chemistry and Physics 58th edition from 1977. So every year they would release one of these, and this would be how you would look up all of the values that you needed to for any kind of chemistry or physics work before the internet existed. So I found this in a bookstore and I bought it because I love this old stuff. And so when I actually was designing this lab, I wanted to find a chemical that would, when dissolved, look how thick this thing is, when dissolved, release a lot of heat. And so what I did is I went into this reference text. First I went to the index. I went to this page. I just marked it, make it quick for me to get there. Went to this reference page and I looked up heats of stuff. These, when it's labeled a heat of something, what it's talking about is how much energy would be released on that thing. What's the energy being traded in this thing? And I went and I found heats of solution. What that means is when stuff was dissolved, how's that energy going to change? And I've already marked that page here too. And so I was able to go to this page, look at the heats of solution here. You see there's a ton of them. It's very fine print. You might not even be able to see it. And I went and I looked through this, and I just looked for one that's when they're negative numbers here, it means that it's going to release that energy. When they're positive numbers, it's going to absorb that energy. So I looked for one that had a nice big number, and I found, boom, potassium hydroxide. And I just happened to have a buttload of potassium hydroxide in the lab. And so I decided to use that. So I wanted to show you this because these heats, these energy changes are generally known values, right? So it's like if I had something like CH4, it would really look like this carbon to hydrogen bond. And what chemists have figured out over the years is that this bond right here, one of these bonds contains a specific amount of potential energy. And if that bond changes to something like water, so H2O, this bond carries a different amount of energy. So they're able to actually go through, count the different bonds in a chemical reaction, figure out how much energy is stored in each one of these bonds, and how much energy is going to be stored in the products of that reaction. So after this reaction goes through, so this plus oxygen like that would make CO2 like this. So these two would combine, plus, add them together, and then would make these two, so plus these two. The energy, the total energy in these bonds, add them all together, and then subtract the total energy in these bonds, and you get whatever energy is left over as heat. So this is how chemists are actually able to go through and calculate these things. In modern times, we're able to just look them up online. It's really easy to find, actually. But in older times, like before the internet, you had to go through and look through this book and look at how much energy is stored in each of these bonds, and then run your calculations and figure out how much heat, how much energy is going to be released.